Welcome to Module 4 and Objective 2. So this is when we're really going to describe more of the aerial photography in this particular section than it is satellite imagery, but we'll get into some of the details. So describe aerial photos and satellite imagery, review some of the methods of acquiring the imagery. So remote sensing has actually been around for a very long time in terms of technology. So one of the earliest examples here is when is the very first aerial photo of in Paris in France, and that was in 1858. So he took up a camera and was like, I'm going to take a picture out of the balloon, and took a picture, and suddenly everyone was like, wow, this is really cool. What more can we do? So there are different ways of collecting the data in terms of what we're actually going to see. So you can collect black and white images. It's not just for the old style way. It actually has a better spatial resolution than the color images. So often we will use black and white images for very precise measurements. You can also get color images, and that's just what we see either as our eyes see, or we can get infrared images, which also just adds that near infrared component to it. So we can use digital or film. For the most part now, you're not going to see a lot of film cameras unless you're working with a very, very small company. Most of them are now digital. They've pretty much all upgraded. And they're mounted in an aircraft for aerial photos, and they fly at an altitude anywhere between 300 to 1300 MASL, which is it should be meters above sea level is what that stands for. Otherwise, if you see MASL, it often can mean mean above sea level. So it's actually meters above sea level. So just so you know that there's a difference between those ones. And so therefore the acquisition height depends on a lot of things. So it depends on topography. So if there's a lot of mountains, obviously you don't want to be too close to the mountain. And safety regulations, for example, you have high rises maybe that show up, or there's other airways that you need to avoid, and also the mission objective. So aerial photos are typically used for small area mapping where high spatial resolution is required. So you're going to see, for example, large scale maps are used with aerial photos. If you're trying to identify, a particular location, such as somebody's house, or you're trying to figure out something like where all the buildings are on a field, out on a farm, and you're trying to do something, maybe some construction around the area. So like a construction project would be a really good example. So individual air photos or mosaics, where a mosaic is where you take your aerial photos and you can put them side by side and they have a little bit of an overlap and it creates one big image. They are used for large scale mapping, like I said, from 1 to 500 or even up to 1 to 30,000. If there is what we call stereoscopic overlap, if there's enough overlap between the photos, we can use those photos to do three-dimensional terrain analysis because we now have enough information to create three-dimensional data. So if we have a vertical, there's technically three different kinds of views that an aerial photo can take. The first one is the most common for mapping. It's like that classic top-down bird's eye view where you're looking straight down, and usually it's within about 3 degrees, and some will argue 6 degrees. So that's the orientation that's going to go straight down the vertical, or it might be off by 3 to 6 degrees. It has a lot less distortion than something called an oblique, so therefore we can use it for mapping purposes because it's easier for us to use for scale. So here's an example that you can see. It looks straight down. We don't really get a sense of any topographic detail, but we can see what's happening on the ground. So then there's oblique. So there's actually two kinds of oblique. There's low oblique and high oblique. Low oblique is when we cannot see the horizon. So it's usually from the vertical number, whether it be 3 or 6 degrees, up to about 30 degrees from the vertical. So it gives us a side view and it still contains the whole thing. Where if you have a high oblique, we're actually seeing the horizon and you can see the sky beyond it, which is kind of what our eyes are. Like we have a very high oblique point of view when we're walking because we can see the horizon with our eyes. So that would give you an idea of a high oblique. So they're usually used to just as a visual aid because they're really not, you can't really do a lot of math with them. You can do something called radial displacement, and you can do relief displacement calculations with them. But again, anything with a scale is a little bit harder to do in the horizontal. So here's an example. So this would be a low oblique image. So you can actually see, oh, this makes sense that there's like a hill here, which is possibly, it would look flat otherwise in a top-down vertical direction. So when it comes to film, there's a couple different kinds. There's the panchromatic, which is the black and white images. It's a fancy name. Panchromatic means that it uses a large amount of the electromagnetic spectrum. And so it says in the visible wavelengths there, but it often blends in with a little bit of UV and near infrared as well. So it has all like a very large bandwidth. And it just comes up with how much total energy that is received by the sensor. So it just becomes black and white. Where in color, we have three different kinds of colors to be represented. So if we use visible light, we have red, green, and blue. That's the color theory that it uses and the model that it uses for that. And so we just see how much has been reflected in those three colors. Then we have color infrared, and so this one adds the infrared side of it, and you can only show three colors at a time. That is a conversation for a remote sensing class. So we can only do three. So that means we have green, red, and infrared wavelengths rather than blue, green, and red. So the red tones relate to the infrared reflectance because the original format of color infrared was it would be an infrared strip for the film, and then it would be green, and then it'd be red, and then it'd be green. So you can think that it actually captures the different wavelengths kind of filters it out as it goes. So we're going to have the longer wavelengths that pass through, so you can kind of inverse what I was saying. So the green is going to be captured first, and it's going to look like it's going to be blue. Anything that shows as green, so if I have like a green turf that I put down that's man-made, it's actually going to look blue in the image. And then anything that has red reflectance, that could be like a red roof, it's actually going to look green. So it kind of mixes it up a little bit, and then the infrared looks red. So it's a little bit hard to wrap your head around until you've actually seen the images. And we don't have any examples in this particular PowerPoint, but when you get to remote sensing, this becomes a really, that's a 451 class. This will make a little bit more sense. So what you really need to pull out of this class is that there's three main kinds of film, or even like digital arrays to be able to capture that image. One is panchromatic, which is just black and white. One is color, or true color, so it looks like what our eyes see. And the other one is color infrared, where healthy vegetation is going to look red. So then there's ways to order this data. So you can get them pretty much everywhere. They're all over the place. So you need a project area. You need to know where it is. You can search the images. And you can figure out what's available in that particular location. Here's, for example, I could say Section 6, Township 25, Range 6, west of the 5th Meridian, which is a Dominion Land Survey address. And then I could try to determine the cost of a 0.4 meter standard color ortho image. So if you want to give that a try and go to the Veltus imagery, I'm not going to work through that example here, but you can imagine that you can go ahead and order your own images if you like and see what the cost of it is. You might be surprised. All right, so acquisition methods. The air photos are acquired in a sequence. And so you fly along, you take photos as you go, right? So, and then you turn around and you take photos as you go, and then you turn around and take photos. So you kind of make this zigzag motion all the way through your project area. And so these parallel flight lines will overlap, but also the images themselves will overlap. So we have an overlap of the images, and then we call something called a side lap, which is that parallel line. So one direction is going to, versus the other is going to have that side lap. And because it kind of creates, or does, it actually creates like a carpet or a quilt of all these different images, then we can actually put them together into one big image, and then we can also use it for stereo viewing. So we try to do flights on a cloud-free day where it's close to noon, so then the shadows are a little bit less. And it could be, that's the biggest reason why we do it at noon. Generally, if you can do it on a day that's kind of that, well, I mean, it says cloud-free, right? So how do you do that without having these long shadows? You can't really do it at night, right? Because at night we need light. We need visible light to be able to see our information. And with no sunlight, we don't have a way to light up the ground. So when I mentioned overlap and side lap, here's what I mean. So if the flight is going this direction, it's going to overlap. You can see that it overlaps here. Now the flight line can actually go back this way. It doesn't have to go in the same direction to have the side lap, just to reduce gas. You will get different perspectives, and those different perspectives are actually really important when you go to do 3D stuff. So that's kind of that offset, which provides that depth. So the objects are viewed from two different angles, and they can therefore be seen in three dimensions. So this flight line does not need to be in the same direction. But you can see what's important here is the amount. So the overlap between the images has to be 60%. The side lap, depending on the industry that you are in, side lap can be as low as 20%, but obviously in this industry, it is 30% in this example. So before you use it in GIS, you need to give it some referencing to ground coordinates. And so there's many different ways that can be done. We don't get into it here. They only talk about georeferencing and orthorectification, but they don't actually talk about the field work that's involved. That is a surveyor's job. So if you do happen to work in this industry and you're working with aerial photos, you will have a field crew, which is the people who are trained in land surveying, to go out and do that. So the referencing methods, we have georeferencing and orthorectification. So to do georeferencing, what it means is reference the aerial photo to known ground control points. And so it's really relatively straightforward with that. And then, but the problem is that it doesn't correct for any distortions, so scale distortions. So I'm trying not to go into too much detail about this because this is like a 2-week talk to really get into the details and nitty-gritty on it. So we have known coordinates. We say, okay, this part of the image or this particular feature belongs here. This feature belongs here. And then we try to stretch and put our image onto the Earth's surface. Now, there are other things that happen because we have elevation distortions, and that's what it's referring to here. So we can use these georeferenced images to take measurements of distances and angles and areas. But we do have to have some caution because not all distortions are taken out. There are some, depending on the math that is used in the background. But otherwise, there are some other ones as well. And those other ones are called geometric distortion and also topographic distortion. So there's some that are fixed in just georeferencing, but the orthorectification really makes it a solid answer. So we get rid of geometric distortion, which is like the triangle when we're trying to take the picture. There can be, like if the plane tilts a little bit, it's going to cause that triangle to kind of go off. So we have to fix that. The photographic scale variations as well, because we're dealing with a curved surface, and any kind of object displacement. So that's like looking at a tower. Even if you have a vertical angle, if that vertical point is not directly on top of, like the center of that image is not directly on top of that that high rise, then you are going to end up with it looking like it's leaning out from the center of the image. So we have to adjust for that. So there is a lot more to it, as you can imagine. So photogrammetry is, for example, a 4-month course in geomatics. And so it really gets down into the details of that. There's a lot of complex math. And then there's orthorectification repositions for each repositioning, is what I should say, to each pixel to correct for the geographic location. Now, georeferencing does reposition every pixel using something called resampling, but in orthorectification, it's just a little bit more mathematically complex for each individual pixel to make it more correct. So they can be used for direct measurement of distances and angles and areas, and that just creates a nice base map that we can use in GIS. So what makes it special is these fiducial marks. So we have these little crosshairs. It's called a metric camera if it has these marks in it, and that each of those marks will tell us the exact information that we need to know about distortions within the camera itself as well. So we can use those crosshairs, and we can use that to orient it outside and inside. So it takes the camera, it takes the orientation of the airplane, and all of that, and it kind of puts it all together. So you can imagine all the math that goes with that is pretty high. So you can, but they're what is key for the orthorectification. And you'll see that some aerial photos will have 4 and some will have 8. So that is a really brief overview of what those look like. So that was about 3 courses worth of information that is really scratching the surface. So just as a summary, the aerial photos can be oblique or vertical. The film that it's on can be black and white, color, black and white, which is panchromatic, color or color infrared. And to help reduce distortions, we need to georeference or orthorectify. And georeferencing has a little bit more, or a little bit less fixing, and the math is relatively easy compared to the orthorectification. But the orthorectification is more reliable, and we can do more measurements with it. So if you want to check out and get some more images on your own and see where they are, then you can go there to these 2 links. There are no exercises, but this is where we really are getting into assignment 2. And there's the references from today. So thank you so much.